Good day, this is the first video in chapter 1.7. We will be talking about cross products. Alrighty, so we've defined scalar product. So you need a scalar and a vector, and it turns it into a vector. For example, the scalar 3 times the vector 1, 2, 3 becomes the vector 3, 6, 9. Then we also have the idea of dot product, or some textbooks call it scalar product, where you have two vectors and you turn it into a real number. So if you have the vector 1, 2, 3 and you dot it with the vector 1, 1 minus 10, it becomes multiply the first components, 1, multiply the second components, 2, multiply the third component, which is minus 30. You add it up, it becomes the number minus 27. So a lot of you have asked, now is it not possible to have two vectors and to define product in such a way that a vector times a vector becomes a brand new vector? And that is the idea of cross product. So can we define a vector crossed with another vector to become a new vector? And the answer is yes. Now the definition is quite complicated, and this is the reason why we are doing it now. Here is the definition. So say u and v are three algebraic vectors. So the components of u is u1, u2, u3, and the components of vector v is v1, v2, v3. So we're going to say vector w, which is also a 3D vector, is u cross v. And I have to tell you how you work out the components. So what you do is, you take vector u and you take components 2 and 3. You take vector v and you take components 2 and 3. So that is my first block. And then what you do is, you take this idea, if you go u2 times v3 minus u3 times v2. So this is the idea of determinants coming in chapter 2. So that is the first component of vector w. And in my second block, I take the third component of u and the first component of u. And then I take the third component of v and the first component of v, and then I do the same thing. The second component of vector w, we call it w2, is u3 times v1 minus u1 times v3. Likewise, for the third component for vector w, I form a third box. And in the third box, I have the first and second component of u and the first and second component of v. And then I go u1 times v2 minus u2 times v1. And this is the third component of w. So it's a very strange definition. So let's just see this in action with an example. So calculate u cross v, where u is the algebraic vector with components 1, minus 2, 1, and v is the vector with components 3, 1, minus 1. Alright, so when I do this, what I normally do is I write down vector u, which is 1, minus 2, 1. Then I repeat the first two, which is 1, minus 2. Then I write down vector v, which is 3, 1, minus 1, and then I repeat the first two components, which is 3 and 1. And then I'm going to work out w, which is a 3D vector. So for the first component, I delete column 1. Then I go multiply that minus multiply that. So 2 times minus 1, which is 2. 1 times 1, which becomes 1, so minus 1. Then for the second component, I now go to the next block. So it's 1 times 3, which is 3, minus 1 times minus 1, so plus 1. And for the third component, I go 1 times 1, which is 1, minus 2 times 3 is minus 6, so minus 6 becomes plus 6. And then it becomes 2 minus 1, which is 1, 3 plus 1, which is 4, and 1 plus 6, which is 7. All right, so please practice this. So if you do this after a while, you become pretty good at working out cross products, all right? So you write down vector u, the first, the second, the third component, then you repeat the first component and the second component. Then you write down vector v, the first component, the second component, the third component, then the first and the second component, and then delete the first column. In that block, work out this funny thingy, and delete the second column, so the first two columns, and in that new block you delete this funny thingy, that is your second component, then you delete 3 columns, and in your last block you do this funny thingy, you get your third component. All right. So cross product, got to practice, and it turns two 3D vectors into a brand new 3D vector. All right. Now here's a shocker. If you've done a lot of examples, even making your own examples, you will see that U cross V is not always V cross U. So the order matters. All right. So U cross V is not always V cross U. So this is a big shocker. All right. So be very careful when you work out cross products. Make sure you know your definition quite well. All right. So the question is, what properties are true? All right. And we're going to turn it into a theorem. So if U, V, and W are algebraic three-dimensional vectors, and alpha is any scalar, so it's a real number, the following are true. So we have that U cross V is equal to minus V cross U. So U cross V is a 3D vector, V cross U is a 3D vector, and they are additive inverses of one another. This is what result 1 says. All right. So even though U cross V and V cross U is not the same, what we can say, this is always true, that U cross V is the same as minus V cross U. Then we have distributive properties, that U cross V plus W is U cross V plus U cross W. Another distributive property, that U plus V cross W is U cross W plus V cross W. And the scalar alpha can jump. So alpha times U cross V is alpha U cross V, or it's U cross alpha times V. So you can put the alpha in front of any vector, or you can first do the cross product and then multiply it by alpha. And then the fifth property, U cross V is the zero vector if and only if V is a scalar multiple of U or U is a scalar multiple of V. All right, and this is going in both directions. The first part implies the second part, and the second part implies the first part. All right. So remember, in 5 we get that if V and U is the same vector, then they are scalar multiples of one another, because then the scalar is 1. So we get a cool result that follows from number 5, is that if you take a vector, you cross it with itself, it always becomes a zero vector. So do it out with some examples, but this is true in general. They're all easy to prove, so give it a go. The biggest tip is we look at components to prove this. So we know that two 3D vectors are equal if the first components agree, the second components agree, and if the third components agree. All right. So the textbook does part 2. So have a look at that. All right. So some more theorems about vectors and cross product. If U and V are algebraic 3D vectors, then the following is true, that U dot U cross V is always the scalar 0. And V dot U cross V is always the scalar 0. Remember, you can only do dot product if you have two vectors of the same size. So U cross V becomes a 3D vector. Use the 3D vectors, you could dot them, it becomes a scalar 0. All right, this is true. We're not going to prove it in this video. Now, a definition. We say an angle is called a right angle if it has magnitude pi over 2. So in our model, we have to redefine everything. All right, so we have to define, what does the word right angle mean? So we define the word right angle to mean if the magnitude between is pi over 2. All right, so more definitions. So say lines with equation L1, which is Q plus T P minus Q, where T is a real number, and line 2, U plus T V minus U, where T is a real number, intersect at single point A. So what we can do is we can form two rays. We can form the ray starting with originating from point A, and we can say that ray 1 is of the form A plus TP minus Q, where T is greater or equal to 0, and ray 2 is T plus U minus V, where T is greater or equal to 0. So we say the lines L1 and L2 are perpendicular if and only if the angle between these two rays is pi over 2. So it is right angled. All right, and the reason why we do this is because ray 1 lies on line 1 and ray 2 lies on line 2. So if you want to know if two lines are perpendicular, so you need the point where they intersect, point A, and then you can form the two rays. And if the angle between the two rays, remember we've done this in an earlier video, it's in the textbook, is pi over 2, then we say that the two lines are perpendicular. All right? And this now allows us to define a new theorem, Theorem 1.7.10. Say u and v are not scalar multiples of one another, and here u and v are algebraic 3D vectors. So if you take rays with equations a plus tu, where t is greater or equal to 0, and ray 1 a plus tv, where t is greater or equal to 0, so the rays to the parameter must be greater or equal to 0. And then ray 2 of the form a plus t u cross v. So here the cross product makes an appearance where t is greater or equal to 0. Then the second ray, R2, is perpendicular to ray 0 and it's perpendicular to ray 1. So we can say that the angle formed by ray 0 and ray 2 is pi over 2, and the angle formed by ray 1 and ray 2 is pi over 2. Alright? So it's good to draw a picture. So ray 0 can be a ray originating from, let's say, point A, and ray 1 could be a ray originating from point A. Then what we can do is we can form a third ray so that the angle between ray 0 and ray 1 is pi over 2, and the angle between ray 1 and ray 2 is pi over 2. The angle between ray 0 and ray 1 can be any angle that we want. Alright, so we now have an ability to form a third ray that is perpendicular to any two given rays, different rays. Alright. This is quite useful, for example, in the right-hand rule from physics. So those of you doing physics would appreciate this theorem. Let's see this in action. Let's look at example 1.7.11. So consider lines L1 and L2, where points P and Q is sitting on line 1, and points U and V with coordinates as indicated is sitting on line 2. Alright, I'm going to leave it for you to verify that line 1 and line 2 intersect in a unique point, and that the coordinates of that point is 4, -2, 7. Alright, so I'm going to leave it for you, do it yourself. The answer is in the textbook, but I want to focus on part B. So we want to find the equation for a line through point A and perpendicular to both line 1 and line 2. So here we have a scenario where the two lines intersect in a unique point. So now we're looking for a third line that passes through this intersection point, and we want the equation for that line if that line is perpendicular to both line 1 and line 2. And then in part C, we want to show that this line is unique. There's not more than one answer to this question. Alright, so let's start off by saying, and well, maybe let's draw a picture. So we have here line 1, here we have line 2. You show that they intersect in point A. Now we are going to find, let's call it line 3, that is perpendicular to both line 1 and line 2. So if you form appropriate rays, the angle between the rays is pi over 2. Alright, so we're doing problem B. So now we can say line L1 is of the form x is A plus t q minus p, where t is a real number, because point A is sitting on line 1 and the line passes through points P and Q. And line 2 is x is of the form A plus t. T is just a parameter v minus u, where t is a real number. Alright, so point A is sitting on both line 1 and line 2, and points V and U is also sitting on line 2. So it is of this form. Alright, now we want the equation for line 3 that is perpendicular to both line 1 and line 2. Alright, and now if we apply this theorem, Theorem 1.7.10, it tells you that if the direction of the one line is U and the direction of the other line is V, then the direction of the third line that's perpendicular to both should be this. So by Theorem 1.7.10, so say by Theorem 1.7.10, we get that line 3 is of the form x is A plus t, and put it in brackets, q minus p cross v minus u, where t is a real number. Alright, so now we got to do the calculation. So q minus p, so you subtract vector q and you subtract it from vector p. So q minus p is 2 minus 1, 0 minus 1, minus 1 minus 2. So that calculation looks like it is 1 minus 1, 3. And then we also got to do v minus u. So v minus u is minus 1 minus 1, which is minus 2. 3 minus 1, which is 2. 3 minus 1, that works out to be 4. And now you got to do the cross product. So we got to do 1 minus 1, 3 crossed with minus 2, 2, 4. That's equal to, take my tip, draw it. So it's 1 minus 1, 3. Repeat, 1 minus 1. Then you draw minus 2, 2, 4. Then you repeat minus 2, 2. Scratch out this times this. So it is 4 minus 4. So minus 4 minus 6. So minus 4 minus 6. Wait. Yeah. So it is minus 1 minus 4 minus 6. It is da. All right. Let me just quickly go back. So the vector is 1 minus 1, 3. And it's minus 2, 2, 4. So minus 1 with 4. Minus 1 times 4 is minus 4. 2 times 3 is 6. Okay, now I can see why it's minus 1, minus 2. This becomes minus 3. So that's minus 3. That's minus 3. I hope you spotted it whilst you also trying this. So this is minus 4 plus 6, which is 2. I hope you agree. And then see how easy it is to make a mistake with cross product. So that's minus 3 times minus 2, which is 6. 1 times 4, which is 4. 6 minus 4, that's 2. And this is 1 times 2, which is 2. Minus 1 times minus 2 is 2. 2 minus 2 is 0. So it becomes 2, 2, 0. All right, so now we can say the answer is of the form x is equal to point A. Point A, did you do that calculation? Do you agree that is the vector 4 minus 2 minus 7 plus t times 2, 2, 0, where t is a real number? All right, so here, by the help of Theorem 1.7.10, we could find the equation for the third line that's perpendicular to both line 1 and line 2. So it was useful to find the point of intersection, which was point A. Alrighty, now, so part B is to show that the answer is unique, that there's not more than one line with this property. Alright, so say line 4 of the form x is equal to A plus TR satisfies the properties. So what we do, this is the tip, we say, let's say there's a fourth line that passes through point A, that's one of the conditions, and that is both perpendicular to line 1 and line 2. It has the properties, all right? So I'm also going to make my life easy, where vector R is of the form R1, R2, R3, where R1, R2, R3 are real numbers. All right. Now, we want line 4 to be perpendicular to line 1, and we want line 4 to be perpendicular to line 2. All right. So we know that the two lines are perpendicular if certain dot products is 0. So we get that from line 1, Q minus P, from line 4, dot R must be 0. What is our reason? Because line 1 is perpendicular to line 4. All right. And so Q minus P is 1 minus 1, 3. And R is R1, R2, R3. So we get that R1 minus R2 minus 3 R3 is equal to 0. We also get that U, so from line 2, remember line 2 and line 4 are perpendicular. So we get that v minus u, always put lines on top of your vectors, that must be 0. So line 2 is perpendicular to line 4. So we get that v minus u is minus 2, so minus 2r1 minus plus 2r2 plus 4r3 must be 0. Alright, so we have 2 equations and 3 unknowns. So I'm going to do equation 1. I'm going to multiply it by 2, so I get 2r1 minus 2r2 minus 6r3, that's equal to 0. Let's call it equation 3. And notice if you go 2 plus 3, we get that this disappears, and so we get that r3 must be 0. Alright? And in 1 or 2, we get that r1 must be r2. So we see thus that the line is of the form x is a plus t r1 r2 r3, where t is a real number. This now becomes a plus t, r2 is r1 and r3 is 0. Alright, so doing the maths, we see that in vector r, the first and the second component must be the same from the maths, and the third component must be 0. Alright, and now we can say, note that vector A is sitting on line 3 and vector A is sitting on line 4. Alright, so we know that this point is common to both line 3 and line 4. Alright, now also have a look at the following. We can easily construct a point on line 3, infinitely many, but in this answer, in this green answer, I can say take t is equal to 1. So if I take t is equal to 1, then I get 4 plus 2, which is 6, 0, 7. So I get 6, 0, 7. So I see also that the point 6, 0, minus 7 is sitting on line 3. Alright, and now in this equation, I can now remember what A is. A is the vector. We worked it out earlier where the two lines intersect. It's 4 minus 2, 7 plus t r1, r2, r1 and 0. I need more space. I hope when you do this question, you have lots of pen and paper. I need a little bit more space to do this. Alright. Now, it is important that if you have a line, that means that r is not the 0 vector. So r1 should therefore not be this number 0. Alright. So now I'm going to do the following. Let's call this equation number 4. We haven't used number 4 yet. So in 4, let t equal to 2 over r1. So we get the vector 4 minus 2, 7 plus 2 over r1 times r1, 0 becomes 4 plus 2, which is 6. We get minus 2 plus 2, which is 0. And we get, that should be minus 7. Minus 7 is also sitting in L4. So A is sitting on both L3 and L4. And the vector 6, 0, minus 7 is sitting on both L3 and L4. Alright, so what have we shown here? We showed that we have two lines, L3, which we found in part B. We found another line, L4, which we said it's a line with some properties that it's perpendicular to both line 1 and line 2, and it passes through point A. But now we have two lines, L3 and L4. But we see that these two lines have at least 2 points in common. So why are the lines the same? Because we found that the two lines intersect in at least 2 different points. So we can say thus, line 3 equals line 4 since they have more then 1 point in common. You can quote the theorem in the textbook, but it is enough to say in words, you found that line 3 and line 4 have more than 1 point in common, so they must be the same line. All right, and that is the end of the story. It's quite a mouthful. All right, so do this question again and make sure that you're comfortable with the logic and also being able to explain it. All right, now as a remark, it is true in general, if two lines L1 and L2 intersect in a single point A, then there exists a unique line through A that is perpendicular to both lines L1 and L2. So we've done it for this specific example, but it's true always in R3. All right. There are some more properties that I want to give special attention to, or just mention so that you are aware of them. Maybe you'll need them in other courses, maybe physics. So theorem about if U and V are 3D algebraic vectors, then the norm of U cross V squared is equal to the norm of U squared times the norm of V squared minus U dot V squared. You can prove it. The proof is a little lengthy, but it's doable. Another cool theorem. If U and V are non-zero 3D algebraic vectors, and say the angle between rays x is tu where t is greater to 0 and x is tv where t is greater to 0 is theta, then the norm of U cross V is the norm of U times the norm of V times sine theta. So what we do here is we form two rays. So ray 1 and ray 2. Ray 1 passes through point U. Ray 2 passes through point V, and the angle between the rays is theta. Then the norm of U cross V has a meaning. It has a geometric meaning. It is the norm of U times the norm of V times sine theta, where theta is the angle between the rays. This is quite useful in mechanics. We're getting to the end of the video. In the next video, we will look at why cross product is really useful. I hope you enjoyed this video. Have a good day. Bye.